The nature of amino acids. Here we see D amino acids and L amino acids, and remember seeing D and L when we talked about stereoisomers. The alpha carbon of all amino acids is chiral with the exception of glycine, because in glycine you have a hydrogen here, and you have a hydrogen over here. And so in glycine, that's the one case where you don't have four completely different things coming off the central carbon, or the alpha carbon, and so glycine is not chiral. But all of the other amino acids are chiral. And here we see the D-alanine, nitrogen on the right, L-alanine, nitrogen on the left, with our Fischer projection. Humans only use L amino acids. Oops. So all amino acids in people will have L configuration in their proteins. But bacteria use D, and so vancomycin binds to D-alanines because that's specific for bacteria, which is one of the reasons why it's such an effective drug against gram-positives, or gram-positive bacteria. How many chiral carbon atoms are in this amino acid? Well, let's look around. This one's not chiral. There's not four things on it. This one has a carboxylic acid, a hydrogen, an amino, and a big organic group. That's definitely chiral. This carbon has two hydrogens, not chiral. And these carbons do not have four things around it. So just one carbon was chiral with four totally different groups on it. Amphoterism. Amino acids can be either acidic or basic, which means amphoteric. An amphoteric substance can act as an acid or a base depending on its chemical environment and what's happening. And so here we see alanine acting like a base. Oh, sorry, they had this backwards. Here we see alanine acting like an acid. It's going to donate that proton to the base to get the salt. So in this reaction, alanine is behaving like an acid and donating a proton. Here, alanine is acting like a base and accepting a proton. And so again, Bronsted-Lowry acids donate protons, Bronsted-Lowry bases accept protons. And so this is the amino acid being basic. It is accepting a proton from the hydrochloric acid. Because there are two different chemical groups, the carboxylic acid group has the capacity to act like an acid, whereas the amino group, the basic group, has the capacity to act like a base. And so that makes amino acids amphoteric. They can be either acidic or basic. Zwitterions formed by amino acids in neutral solutions. And that's a German word, Zwitterion. And basically it means there's two different charges on the same molecule. Here, the amino group grabs a proton at pH 7 and the carboxylic acid group releases a proton at pH 7, producing the zwitterion. Still neutral charge, just the proton transfer from the carboxylic acid group to the amino group to have a positive and a negative charge in the same molecule. And zwitterions can act as an acid or a base. Here we see it acting as an acid. It's donating a proton. So it's reacting with the base. Here we see it acting as a base. And it's accepting a proton. So it's grabbing this proton and accepting it. Isoelectric point. This is the pH at which there is no net electric charge on an amino acid. And the isoelectric point is between pH 7.8 to 10.8 for basic amino acids, between 4.8 to 6.3 for neutral amino acids, and between 2.8 to 3.3 for acidic amino acids. And this class doesn't really go too much into the pKa versus pH, but basically, when the pH of a solution is at the pKa of the acidic or basic group, it's basically half protonated. So here we see the pH at the isoelectric point for each amino acid's moiety. So at that pH, that amino acid is exactly no charge. If it gets more acidic, it'll start grabbing protons and it'll become positive. It becomes more basic, it'll start losing protons and it'll become more negative. So draw the structure of L-phenylalanine in its Switterion form. Well, here we have D-phenylalanine. Oh, sorry, that's L because the amino group is on the left, like in the L form. And here we have our Switterion. And now if it reacts with a really strong base, you'll remove this proton from the amino group and you end up with a negative charge. And so again, if you put phenylalanine in a very basic solution, you end up with a net negative charge. As you get closer to neutral, you gain the proton back here and it becomes a neutral compound. And if you get more and more acidic, like we hit pH 1, now this area will protonate, but you'll still have the positive charge on nitrogen, so you'd have a net positive charge. So again, in basic solutions, when you're way more basic than the pKa of the molecule, you'll be negative. Then there's a neutral range, and then in superacidic conditions, an amino acid will be positively charged. Peptides. When multiple amino acids bind together, we have a peptide bond with a peptide linkage, and it is an amide bond. Notice, carbonyl with nitrogen. We remember seeing this with the amides. That is a peptide bond, and it is an amide. And the peptide bond is really right here in the amide. But we circled this carbon group and this nitrogen to show you have two substituents coming off of your amide. So this is a dipeptide, 2 amino acid units. A tripeptide has 3 amino acid residues. A tetrapeptide has 4, penta is 5. And polypeptides, it's like 40 to 50 amino acids. And if you get more than 50, we just start calling it a protein. It's a much longer chain of amino acids. So representing peptides, the N-terminal residue end with a free NH group, and that's written on the left. So the N-terminus, the beginning amino acid is always on the left, and we keep writing out the amino acids in linear order until we get to the C-terminus, which will have the free carboxylic acid group. If any segment is not specifically known, it gets put in parentheses. And that lets the reader know it's not specifically known. Naming peptides, acyl derivatives of the C amino acid. So, the C-terminal residue keeps the name. So here we have a glycine, and then we start naming it in order from left to right. An INE ending becomes YL. So alanine, tyrosine, glycine becomes alanyl tyrosyl glycine. So again, the C-terminal residue keeps its name. The glycine here is a C-terminal residue. It has the free carboxylic acid group, making it the C-terminus. And so glycine stays as glycine, but alanine becomes alanyl, and tyrosine becomes tyrosyl, because the INE ending becomes YL. Alanine and glycine can form 2 different dipeptides, glycine-alanine or alanine-glycine. Different N-terminuses, different C-terminuses, not the same polypeptide. If 3 amino acids combine, you can have 6 tripeptides. So you can have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. You get 6 possible combinations because the first spot and the third spot are not the same. The N-terminus and the C-terminus are not identical because the N-terminus has a free amino group, whereas the C-terminus has a free carboxyl group, and therefore they're not equivalent. And so it's a permutation as opposed to a combination when we look at how many different ways they can combine. So the functions of peptides, many of them are hormones. Some of them are nerve transmitters. We have substance P, which is a pain-producing agent in the body. Bradykinin affects tissue inflammation. Angiotensin, this maintains water balance and blood pressure. Vasopressin, here we increase blood pressure and decreases kidney water excretion. Oxytocin, that is a hormone that initiates childbirth labor and causes mammary glands to release milk. We see thyrotropin releasing hormone. This stimulates the release of hormones from the pituitary gland. Orexin causes wakefulness. Neuropeptide FF modulates pain sensations. Neurotensin is involved in brain memory functions. It's not totally understood exactly how, but we can see it is definitely involved. Neuropeptide Y stimulates eating. Endomorphin acts as a morphine-like analgesic in the brain. And so again, peptides function in many, many different capacities, and a lot of them are hormones. Write the structure of the tripeptide alanylcystylserine. So we have alanine, cysteine, and serine. And then we combine them all. And when you make a peptide bond, you excrete water. And you get amide bonds. And there we have our amino acids with our peptide bonds. You are given the 2 amino acid molecules shown below. How many different dipeptides can you make from these 2 molecules? Draw these structures. They give you an alanine and a glycine, so you can have 2 different possible polypeptides, either with the alanine as the N-terminus and the glycine as the C-terminus, or the glycine as the N-terminus and the alanine as the C-terminus. So it can be alanine glycine or glycine alanine. They are not the same thing. So it matters in this case. Proteins. You need at least 50 amino acid units to be a protein. And to serve a specific biological function, a protein requires a definite shape. And we describe proteins on 4 levels. The primary structure, which is just the linear order that the amino acids are linked together. The secondary structure, this is the folding that is only due to hydrogen bonding. Secondary structure is 100% due to hydrogen bonding. And that gives us alpha helices and beta turns and beta sheets. Tertiary structure is the final 3-dimensional structure of a single polypeptide. Because I say if because not all proteins have multiple polypeptides, but if there are more than one polypeptide, like hemoglobin has 4 polypeptides, then quaternary structure is the final structure of how the multiple polypeptides fit together. So if you have a protein that only has 1 polypeptide, then you don't have quaternary structure. You need multiple polypeptides combining together, like hemoglobin, which has 2 alpha units and 2 beta units, to have true quaternary structure.